project for open source 2D and 3D drivers for the Freedreno GPU and Snapdragon SoCs and some others. So my initial motivation is very much the same as Luke's and many other people who've done projects to look up graphics hardware. In my case, I don't have any binary block drivers for generic Linux, only for Android on these devices. If I want to run something different, anything kind of stuff.
Can you speak up a bit?
Yeah, possibly. I can try. So, I say on these devices, only Android binary blobs are available, and if you want to run Linux and X and so on, you're kind of stuck. So, a bit of the history. So, Freedreno is actually two completely separate cores. I mean, they share an MMU, but as far as how they work, they're just different. The 2D core, it's, I believe, originates from BitBoys. That's my theory. That's what I started working on first. So in March of last year about, I started working on some code to intercept the command stream, start decoding and figuring out what it's doing, and start writing a basic EXA driver for XOR. More recently, I've been spending more time on the 3D side of things. So just started barely poking at it back in April, but getting a little bit more serious and making some more progress by June. Shader disassembler in early July, and after I figured that out, I wrote a shader assembler, which is what some of the early 3D demos were using. And then back in November, I started on the Gallium driver for Freedreno. So maybe I should have put this slide previous. So yeah, the 3D core, the origin is ATI AMD. You can kind of think of it as, there's R300, R600. It's something different. I mean, it has the same level of similarity to R600 that R300 is. It's a tile-based renderer, but the management of rendering within a tile, it works much like an immediate mode renderer, and the management of the tiling is all done on the driver, not really in hardware so much. Whereas most tilers like Mali or SGX are using a small, like 16 by 16 or 32 by 32 tile. Freedreno is using something larger. It's using a little piece of memory inside the GPU core that ranges from 256K, half meg, something thereabouts, depending on the version. And inside that buffer, you have the current piece of the color buffer that you're working on, as well as depth and stencil. From looking at their kernel driver, it seems like some of the newer Snapdragons, they replaced GMEM with something they call on-chip mem, which can be actually partitioned dynamically, it seems, between other accelerators like video decoding code. So the 2D core, that's a Z180 or Z160, depending on the chip. Different Freedreno versions have anywhere between 0 and 2 2D cores. So the one I'm working on has 2 2D cores. Others have none. I think some have one. But it's got a completely different command parser format. On the 3D side, I guess you could say the top level command stream format is the same as the Radeon stuff. It's command like write this value to this register or do this opcode. The format of the The payload, let's say, of that is all different. The header is kind of the same. So what have I used for this? The very first thing I wrote in the very beginning was creatively named LibWrap. It's basically a preload shim that intercepts ioctals, intercepts memmap, and a few other system calls. Keeps track of all of the graphics buffers that are allocated, keeps track of the command submission, and a few things like that. And then it just dumps that into kind of a simple command, type, length, value, file format. Redump was the first tool I wrote that does something with this format, and that was to parse the 2D command stream. And what I did in that case actually is it had some logic to do side-by-side diffs of the command stream and highlight differences. So I basically just wrote a bunch of tasks where I could vary like width and height and stride and all these different parameters, and then just look where they show up in the command stream. So CFF dump is the parser tool I use for the 3D side. It's somewhat more sophisticated. It can follow GPU pointers that it finds in the command stream. So, I can capture the contents of a vertex buffer or things like that, which were useful, especially early on, to find, oh, this is where the vertex buffer fits. This is where, the other reason I need that is because the indirect branch is used a lot by user space. So the command stream ends up having a lot of branches in it, and when I'm parsing the command stream, I have to find that branch and follow it into a different buffer and then parse from there. Over time, that got hooked up to the shader disassembler, so it would inline disassemble the shaders that were used and stuff. It's quite useful for me. When I started looking first into the shader assembly, I wrote a tool that would parse the output of the GLOES get program binary extension, and a test program that I could just feed it a bunch of shaders that have small differences, like a different squizzle, or addition versus subtraction, or things like that. And that's what I used to start figuring out, okay, how big are the opcodes, how big are instructions, where does register value show up, things like that. And then, in some ways, like Lima, before I started up the Gallium driver, I wrote like a simple GL-like standalone playground, which is what the rotating cap and some of the other earlier demos used. And that gives me an easier way to experiment. It doesn't have a shader compiler, it just uses the assembler. I can directly try out different things in the shader, for example, and see how that works. So this is a quick screenshot of what I spend a lot of time doing with the CFF dump output. So it shows you, parsed out register values and things like that. And then one thing I found very useful is on the draw opcodes, dump all the current register values because it's keeping track of them as it goes. And then I could look at two different draw calls, like, for example, with a binary driver versus mine, and see, oh, these registers have different values. But somewhat useful. So a bit about the 3D, and I'm trying to run this fast because we don't have a huge amount of time. So I mentioned the tiling, the depth, Z and color buffers sit in GMem, not really side by side, but one after the other. Rendering is done in passes essentially. You have, well, I'll show you on the next slide. Slides. So the first level command parser, like the type 0, type 3 headers, those are the same as R300, R600. Registers, there's a few similarities. mostly different. All the PM3 opcodes are different. Eventually, after I had the kind of rotating cat thing working, it was October timeframe or something like that, or September, a little bit earlier, I found a older version of the kernel driver Freedreno kernel, which had a lot more register and bit fields in the kernel, which was, and also a description of what the instruction set instructions were, which was pretty useful. I mean, I had a pretty good idea of that at that point, but I, had a few mistakes, a few places where I wasn't sure about the size of a bit field or whatever, off by one bit, or, sort of stuff. So, back to the way we deal with tiling. Essentially, we have one command stream buffer that we build up in user space like a traditional GL driver. As the clear and draw VBO and stuff comes into the Gallium drivers, it emits commands into that. And then finally, when we need to flush, what actually happens is we have a little bit per tile command stream that does an indirect branch back to the clear and draw calls for each command. So per tile command, we have to, optionally or potentially, we have to restore the old tile contents, like bring it back from system memory into the tile buffer. We have to do that if there's not like a GL clear call. If there's a clear call, we know, hey, we don't need these old contents, so we skip that. And then same goes for the bit color and depth scissor. It sets up a window offset to say, hey, I'm rendering this part of the tile. It sets up the scissor, and then indirect branch to the clear draw, and then it moves the contents back out of the system memory. So there's a little bit of fun in that because the restore and resolve parts actually dirty some of the state, so you have to kind of keep track and know that some of the state, because we're not executing the command stream in the same order that it's built. We build the tile commands first, long after we've done the clear and so on. So we kind of just need to know ahead of time that certain bits of the state are going to be dirtied and always re-emit them on the first draw. So something to got to kind of remember, take into account, but it's not that bad. So the instruction shader instruction set is unlike the Molly stuff and the Tegra 2.3, it's a unified shader. So that was nice for me. I only had one instruction set to figure out instead of two. And it was also nice because I figured out pretty early on instructions were fixed number of bits, so I could pretty easily find where the one instruction starts, one instruction stops, figure out where the registers are, or specified register numbers are specified, and so on. So that was very nice and easy compared to what Connor's going to talk about next. So right now in the Gallium driver, I have a very bone dead simple TGSI to native translator. Essentially, it doesn't do any optimization. It doesn't try and reduce the number of registers used or anything like that. So that will come in time. Okay. So the instruction set does have some similar concepts that would say to R600 and later. You kind of have two parts to the program. The first part is the control flow essentially, and then the control flow refers out to ALU instructions that come later. Like this is how it's laid out in memory. You have exec, out, end exec, and no op. But this exec actually points to these three instructions, and the exec end points to these next two. So conceptually, it's this order, memory of this order. I think that helps the hardware figure out how to schedule things. Okay, so status. So far, up till now, I've mainly been concentrating on what's basically a Snapdragon S3. It's the A220 Z180, and that's because that's what I have hardware for. I will actually very soon have a Nexus 4 with an A320, so I'll start looking into different versions of the GPU and adding support for those pretty soon. I think some of the earlier stuff, like the A200, Z160, that's in the Freescale IMX5, looks like it should be pretty similar to what I mean, the kernel driver with the, some of the registered bit fields and names and stuff is actually from the A200, not from the A220. But so far, I've only found a few places where it disagrees from what the A220 actually is. Exit support is basically there. Some things need debugging, some things are missing, like composite ops with the mask surface. I think pretty much everything's understood there. It's just a matter of time to implement and debug. On the Gallium side, that's where I've been spending most of my time now. I would say that more than half of GeoMark 2 works now. XBMC works. Compiz itself works. Some bugs with some Unity stuff. Quake 3A basically works. Quake 3 Arena. A few things still needed. I need to add support for MSAA and for map textures. Compiler, I think the main thing that I haven't added yet is loops. It's got if-else stuff and enough instructions translated. And then there is some hardware binning support which can optimize it a little bit. The tiling, the Qualcomm calls it binning, which I'm not using yet. I think that will mainly be a win for cases where you have huge amount of vertices. So, what I will do now, hopefully, is demo some stuff. So, I don't actually have this works. The backlight code in the video driver in this is just really horrible, so the backlight doesn't always come on. There we go.
Super, make me a sandwich.
Yeah, okay. Unfortunately, this is going to take a few minutes. Yeah, some things don't work quite right when you kill and restore text. So, and unfortunately, this takes a while. So, while we're waiting for that, any questions?
So I saw that one of the things still on the list is
are you expecting there to be weird interactions with the tiling architecture and delayed MSAA resolves?
I think
Cause
there's one thing that I was thinking about a little bit that I could optimize a little bit, which might be hard with Gallium. I can do the MSAA resolve and the GMEM to system memory in one shot,
right.
without having to do a separate pass.
Only for the back buffer though.
Pardon?
Only for the back buffer though.
Well, I would end up having, unless I had some way to know that I don't need the back buffer in the next frame, I would have to do the memory to the GMEM to system mem twice.
You know, I was referring to if you render to make multi-sample the texture, then you obviously need access to the
right.
samples.
Right.
Sorry.
So, yeah.
Well, but multi-sample textures is an optional feature. Maybe on hardware where that would be a super hassle, you just don't expose that.
Well,
Yeah.
multi-sampling in general is an optional feature in OpenGL, yes.
Technically it's optional, but everyone will hate you if you don't support that. It's optional for the spec, but apps want it.
Technically, OpenShell is optional.
Yeah.
Yeah.
So,
One question.
mm-hmm.
Do the Arduino, does it have a fixed firmware, or is the firmware loaded on boot up?
The firmware is loaded at boot up. I haven't really looked at decoding what that firmware is.
Could it be possible that it's actually a general purpose GPU? If so, would it make sense to try port Linux to it, if you understand what?
It's not, I think it's probably more closer to what firmware does in like Radeon or something. I think it's something, it's not like SGX where it's, or Radio Core stuff where it's like a general purpose. Okay. So the other fun thing is I don't actually have HDMI out on this. So what I'm going to attempt to do is show it on camera for the people in the back.
Brings back a memory.
Pardon?
Brings back some memories.
Right. Let's start synergy on this. Okay. Well, if I can't get synergy to work, I can't yet show wobbly windows, the exciting must-have feature. So, show here. And people can come up after and look at it. So having the mouse operate just from
Just hold it upside down.
So, compass is mostly working except for some a few Unity-isms, but lovely it does. So, XBMC itself works, although it takes a minute to start.
The burning windows?
Pardon?
The funny burning windows of Ubuntu? When you close them?
Sorry, I didn't catch that.
Not that important.
I haven't tried all of the Compass plugins.
Ah, okay.
Tried some.
Yay.
So, turn this off real quick. So there's still some room for improvement on the performance side of things. I haven't really focused too much yet on performance, but you know, you can watch your giant oversized body, except for. By the way, that crash was actually the baby, not Gallium driver, surprisingly enough. It sometimes crashes. It started video playback for some reason.
Oh, Rob, you're running into Connor's time.
Pardon?
You're running into Connor's time. So maybe something quick.
Yeah, pretty quick. The last thing I was going to show you
I'll see that one up close later on because I spend a lot of time watching this stuff up close. Oh, I can't even do that. Oh.
Now the text has the right color.
yeah, the input on this is all kind of messed up. The guy seems to like run forward by default.
Yeah, it's just this cheat stuff from Oliver.
Oh, is it?
Yeah.
So, yeah, I don't know how to do anything about that, but yeah. And now I'll get out of Connor's way before he gets.
You're still telling the driver you only have one texture, right?
No, I can support things with multiple textures.
Because Oliver has code as a bug there.
Okay. I don't know. I haven't looked too closely at what Quake uses, but I have other stuff that's using multiple textures.
Okay. It brings a lot of performance. It's like 5 frames for me. Multiple textures or not, so it brings 7 more.